video class. So in this video, we are going to see UV visible spectroscopy. This is a typical UV visible spectrometer. So this is working under the principle, and the black diagram of this UV visible spectrometer is given. Here two mirrors are used. One is deuterium lamp, another one is tungsten lamp. Deuterium lamp is for visible region and deuterium lamp is for UV region, and tungsten lamp emits light in the visible region. So all the lights will pass through the filter, and after the filter, the monochromator will pass the UV and visible region of light in a growing order of wavelength to the sample and the reference. So in the output, we can record the spectrum. So this UV spectroscopy, there is two important principles. One is Lambert's law, another one is Beer's law. According to Lambert's law, when a beam of light is allowed to pass through a transparent medium, the rate of decrease of intensity with the thickness of medium is directly proportional to the intensity of the light. So the intensity decrement is directly proportional to the thickness of the medium. So according to Lambert's law. So according to Beer's law, the intensity of beam of monochromatic light decreases exponentially with the increase in concentration of the absorbing substance also. So the Beer included the concentration of the absorbing medium also. So the UV visible spectroscopy, so working on these two laws, working based on these two laws. The first law is Lambert's law and the second law is Beer's law. So according to Lambert's law, when a beam of monochromatic radiation passes through a homogeneous absorbing medium, the rate of decrease of intensity of radiation with thickness of the absorbing medium is proportional to the intensity of the incident radiation. So the incident radiation, definitely when it falls through a absorbing medium, the medium will absorb some amount of light, and only lesser amount of light will comes out of the medium. So the lesser amount of light and the absorbing through the absorbing medium is the decrement in the intensity is proportional to the thickness of the absorbing medium. So it is a Lambert's law. And after that, Beer introduces the concentration term also into this law. According to Beer's law, when a beam of monochromatic radiation passed through a solution of an absorbing medium, the rate of decrease of intensity of radiation with the thickness of the absorbing medium is proportional to the intensity of the incident radiation as well as the concentration of the solution. So in the Lambert's law, the decrement in the intensity of the incident radiation is directly proportional to the thickness of the absorbing medium alone. And Beer introduced the concentration term also. So according to Beer's law, the intensity decrement, the decrease in the intensity of the incident radiation is proportional to the thickness of the absorbing medium and also as well as to the concentration of the solution. When the solution is more concentrated, the absorption will be more. So we can get only a lesser amount of radiation which comes out from the medium. So what happens to the light which is missing? So the missed light was absorbed by the absorbing medium. The absorbing medium, after absorbing the light, it will get excited. Yeah. The absorbing medium after absorbs light, after absorbing the UV and visible region of light, the electrons in the molecule get excited. So there are the electrons in a molecule can be classified into three types. One is sigma electron, another one is pi electron, which is available in the pi bond. The sigma electron is available in the sigma bond, and the third case is non-bonded electrons. So this is the energy diagram of all the bonded electrons. So the lowest energy is sigma bonding orbitals. and the next one is pi bonding orbitals, and the next one is non-bonded electrons, and the fourth one is pi star, which is pi anti-bonding orbital, and the fifth one is sigma star, that is a sigma anti-bonding orbital. So the electrons in the initial state before we are passing the UV region of light and visible region of light. So the electrons can be occupied either sigma bond in the molecule or pi bond in the molecule, or it will be as a non-bonded electron in above the available in the certain heteroatoms in the molecule. So while you are passing the UV and visible region of light, so there are 4 types of electronic transitions or electronic excitations possible. So we have seen in the Beer and Lambert's law, the intensity of the light decreases when we are passing through the absorbing medium. So the intensity of the light decreases when we are passing through the absorbing medium. So what happens to the absorbed light? The absorbing medium or chemical compounds, after absorbing the light, the electrons in the molecule, either sigma bonded or pi bonded or non-bonded, get excited to the higher energy state. So this kind of electronic excitation is possible once the molecule absorbs UV and visible region of light. In the first case, the sigma to sigma star excitation is possible, and the second case n to sigma star excitation, and the third case pi to pi star excitation, and the fourth one is n to pi star excitation. So the energy required for the excitation, so this is the energy order. So the energy required for various transition are in the following order, where sigma to sigma star transition requires more energy because the distance of the energy level is more. So sigma to sigma star requires more energy, and the second thing, n to pi star requires lesser energy when compared to the sigma to sigma star, and the third case, pi to pi star transition, which is lesser energy than the other two, and the last one is n to pi star transition. So here this is the energy order of the 4 types of transition. First case is which is having required more energy is a sigma to sigma star transition, and the second case n to sigma star transition, and the third case pi to pi star transition, and the fourth case n to pi star transition. These are all the 4 energy requirements for the electronic excitations. So in the first case, let us see the first case. This is sigma to sigma star transition. Here it is a high energy process since the sigma bonds are in general very strong. The organic compounds in which all the valence shell electrons are involved in the formation of sigma bonds do not show absorption in the normal ultraviolet region. So in this case, so look at the diagram. Here we have given only C single bond C. So the carbon valency of carbon is 4. Other 3 valencies you can don't consider right at this moment. You consider only the bond between the 2 carbon atoms. The CC bond, the bond is denoted, the sigma bond is denoted by using 2 electrons. So 2 electrons lie in between 2 bonds. The single bond can be created by the mutual sharing of 2 electrons from the 2 atoms. So each electron shared each carbon sharing 1 electron. So to make a sigma bond. So during the transition from the sigma bonded electron, 1 electron moves to the sigma star. So it is denoted in the picture. The 1 dot, that is 1 electron, moves from sigma bonding orbital to sigma star anti-bonding orbital. So this kind of transition is called sigma to sigma star transition. So the second type of transition is called n to sigma star transition. Here there is a single bond between the carbon and heteroatom. On the other hand, the heteroatom like nitrogen, oxygen is having lone pair of electrons. So lone pair in the sense it is not bonded with any other atom. So it is having non-bonded electrons. So though sigma bond is there, the heteroatom which is denoted as X is having non-bonded electrons. Here in this case, the electronic excitation happens from non-bonded electrons to sigma star. It is having only sigma bond, there is no pi bond. So once a sigma bond is there, definitely sigma star anti-bonding orbital also will be there. So the electron from the non-bonded lone pair of electron from the heteroatom, one non-bonded electron moves from non-bonded electron state to sigma star anti-bonding orbital of sigma. So this kind of transition is called n to sigma star transition. And the third type of transition is pi to pi star transition. In the pi to pi star transition, there should be a double bond between two carbon atoms. Normally, the first bond created between two atoms should be definitely a sigma bond. The second bond only happens to be a pi bond, because the second bond created by the lateral overlapping of the two electrons from the two atoms. So here, in this case, if you consider this carbon-carbon, here we have denoted the two bonds between the carbon-carbon by using 4 electrons. First, initially, one carbon is giving 1 electron, and another carbon is giving 1 electron. That creates a sigma bond. And the carbon is giving second electron, and the other carbon also giving a second electron to create a pi bond. So here, between the two carbon atoms, two bonds will be there. One is a sigma bond, another one is pi bond. Now, in this type of electronic excitation, which is nothing but pi to pi star electronic excitation, the sigma bond will not get disturbed. So, which is the first bond, strong bond, will not get disturbed. Only the pi bonded electrons, one electron moving from the pi bonding orbital to pi star anti-bonding orbital. So, this kind of transition is called pi to pi star transition. So the last transition is called N to pi star transition. It happens in the case of ketone-like compounds. Here the valency of carbon is 4. So the carbon is having bond with the other two alkyl groups in the left side. Now you consider only the C double bond O case. So only you consider this bond C double bond O. The first bond between the carbon and oxygen is a sigma bond, and the second bond between the carbon and oxygen is a pi bond. In addition to that, the oxygen is having lone pair of electrons, which is a non-bonded electron. So in the fourth type of transition, the non-bonded electron moves from the lower energy state to pi star transition state, higher energy state. So here there is a possibility of N to pi star transition. The non-bonded electron which is available in the oxygen will go to the pi star orbital, anti-bonding orbital of the pi star anti-bonding orbital. So this kind of transition is called N to pi star transition. So we can have a look at all the 4 types of transitions with the examples in this case. The first type of transition is having more energy. It is nothing but sigma to sigma star transition, which happens in normal alkanes, which is having carbon-carbon single bonded compounds. And the second case is N to pi star transition, which happens in the case of ketone-like compounds. And the third one is pi to pi star transition, which happens in the double bonded carbons, where along with the sigma bond, one pi bond has to be there. Then only pi bonding orbital and pi star anti-bonding orbital will be available for transition. And the fourth case is N to pi star. It happens in the case of N to pi star happens in the case of ketone-like compounds, where the energy level is very minimum. So the non-bonded electrons from the oxygen will get excited to the pi star anti-bonding orbital. The second case is N to sigma star. The first case is sigma to sigma star. The second case is N to sigma star. The third one is pi to pi star, and the fourth one is N to pi star. These are all the 4 types of transitions possible while you are passing ultraviolet and visible region of light to the chemical compounds. So these are all the 4 types of transitions possible: N to sigma star, sigma to. These are all the These are all the four types of transition possible when you are passing UV and visible digital light to the chemical compounds, molecules. So first one is the sigma to sigma star transition, second one is N to sigma star, and the third one is pi to pi star, and the fourth one is N to pi star. So set of examples has given. Sigma to sigma star, as I already told, it happens only CC single bonded compounds. So for example, methane, it is happening in the methane. And the second case is N to sigma star, it happens in a compound like oxygen, nitrogen, heteroatom available compounds. Example is alcohols, ethanol, water, all those compounds is the example for N to sigma star. And pi to pi star happens in the case of double bonded compounds, alkenes. In the alkenes, N pi to pi star transition is possible, and the carbonyl compounds, ketone C double bond O carbons, along with the sigma bond and pi bond, non-bonded electrons available on the oxygen. So in this case, N to pi star transition is also possible. Thus, we have seen all the four types of transitions possible while we are passing UV and visible region of light to the chemical compounds. The first transition with more energy is the sigma to sigma star. The second transition with somewhat little energy is N to sigma star. Then the third transition with lesser energy is pi to pi star. And the fourth one with the least energy requirement is N to pi star. Thank you.
இந்த வீடியோ உங்களுக்கு பிடிச்சதுன்னா லைக் பண்ணுங்க, ஷேர் பண்ணுங்க, கமெண்ட் பண்ணுங்க, சப்ஸ்கிரைப் பண்ணுங்க. மறக்காம பக்கத்துல இருக்க பெல் ஐகானை கிளிக் பண்ணுங்க.